question.
I know you don't like the decision. I have a job. Are they gonna test tomorrow?
I like 4 or 5 tests.
First,
Is it coming out?
first
Sure.
3 at 2
Well,
or
if we
3.
get break up in 2 days, you can be done with this.
Yeah, but that's coming in after church,
Yeah.
not skipping church.
I don't, I'm just saying.
What was that?
That's always well. Don't get tired that night.
Go ahead today.
You're tired that night because of church?
No, because it's the day of week.
This is late when it
And
comes
then you
after
wake up
church.
early.
Very. So try to go to 11.
What time do you go to bed normally?
Actually, like,
Like midnight.
Most of the time, other than a couple nights.
Yeah, but we stay really long.
well, like by the time we get home, it's like 11. And
The latest said like 10,
New 10.
And that was like, what, like pretty late. for
That was the
normal.
very first one.
Normally, we're out
well,
here.
when it's after,
Well,
when
one
it's
time I
after
went to
one
basketball.
I usually stay till like.
Oh, I didn't stay for that one.
Never stay till
I didn't realize anyone was staying.
Oh,
You're
yeah.
only-
No,
No, there's no way.
We went to the gym.
10:30?
I realized
I
that
think
like,
one
the next day.
We were here at
That was the run, where'd you leave? Like, I didn't know you were going to the gym.
There was
I
one,
mean,
so we
one
got
time
here.
it was because they were playing basketball.
The very first time.
All right. So, there's there are two ways to find or determine the equivalence point of an acid-base titration. The first way is probably the easiest way, but not something that is really practical for our certain situations. Use a pH sensor. Okay, use a pH sensor to monitor pH curve. And where do we know the equivalence point is on a pH curve?
The vertical.
In the middle of the vertical section. Okay, we would do this in a lab. We would use a burette, we would add a drop at a time, and we would let the pH stabilize. We would keep the data, and it would produce a nice pH curve. And in the middle of that pH curve is approximately where our equivalence point was. And remind me what the equivalence point is?
It's when.
completely neutralized.
Yeah.
I probably shouldn't say the word completely neutralized. What I probably should say is that's where we have used up or reacted all of our original substance.
I have not. yet.
Because technically, when you think completely neutralized, I would normally think a pH of 7, which if it's a strong situation, yes, that's how it works. But when you're doing a weak titration, it always produces a conjugate. So technically, we're not completely neutralizing it. Okay? The second method, and we use this, we actually a lot of times use both just to kind of get practice with how an indicator works. We would use an indicator. What an indicator does is it marks the endpoint of a titration by a change in color. Okay? Now don't think that endpoint and equivalence point are equal. I'm going to write that. Endpoint does not mean the equivalence point. However, if you use an indicator correctly, the end point can virtually be the same as the equivalence point. Here's what I mean. Let me define what an end point is. An end point is when your indicator changes colors. And you're probably like, well, that doesn't mean much to me. Yeah, I know. I'll explain how indicators work in a little bit here. However, if you do it right and you choose a correct indicator, you can get the color to change at the equivalence point or close to the equivalence point. Does that make sense? Okay? And it takes some practice getting to know how we choose an indicator, but we'll kind of go over that here in a little bit. So we're going to talk today about acid-base indicators, how they work, what goes on with them, and so forth. So, what is an indicator? Okay? An indicator is a substance that marks the endpoint of an acid-base titration by changing color. Okay? And this should make sense. When choosing an indicator, you want the color change of the indicator to occur approximately at the pH of the equivalence point, so that when you see a color change, you know you're where? What was that? Well, at the equivalence point. We know that I have completely gotten rid of my original stuff. Okay? So that we know we're at a stopping point, so I know I can start doing some math to figure out what the concentration of my unknown thing was. Okay? Now, we set a pH curve a lot of times looks approximately like, that's too steep right there. Start at a point and you kind of hit your buffer region and then you see woofta. It goes like that. Okay? And we said the equivalence point is approximately right there. In fact, I could probably make that steeper and it would be more accurate. Okay? So, what do you notice about this region here? You're not adding a whole lot to get a huge pH change. Okay? So, if you set your indicator correctly, your color change could actually happen here, and you might be thinking you're way far away from the equivalence point, but in reality, have you added a whole lot more or a lot less volume that really you'd be that far off from your equivalence point anyways? No. So I could have a color change happen here and only be off by like 3 or 4 drops. Does that make sense? Okay? Now obviously if you completely butcher what indicator to use and it starts changing color right here, we have a problem. Okay, but we'll talk about this. Okay? So our indicator doesn't have to be exactly perfect because of the nature of what happens when you're neutralizing an acid or a base. So let's spend the rest of the time breaking down how an indicator works. So I'm going to generically write an indicator in acid form like this. Does that make sense? Why I would use that to abbreviate the acidic form of an indicator. IN refers to indicator, H means it has an acid, or has a proton connected to it. Alright? Basically what indicators are typically a weak acid that has one color in its acidic form and a different color in its conjugate form. So there's acidic form of the indicator, basic form of the indicator. So let's say we're using, this is actually a really common indicator known as phenolphthalein. It is colorless in its acid form, and when it's in its base form, it's pink. And we can choose a variety of different indicators. Some indicators might be red in one form and blue in another form, or yellow in one form and green in a different form. There are lots of different types of indicators, and we'll actually look at a page in our book that kind of gives us a huge list of indicators. Okay? So, if I were to write the Ka expression of this, like this. Now, let's say that we have a pH of 1 in this particular situation. What's the H plus concentration of that? What was it?
10.
I still like your
10 to the negative 1.
Yeah, okay. I just hear 10 to the negative and then you draw it off. Okay? The Ka for this particular indicator is 1 times 10 to the negative 8. It's the Ka for this indicator. So what I'm going to do is I'm going to solve solve so that I just have my ratio of my indicator components. So I have 1 times 10 to the negative 8 over 1 times 10 to the negative 1 gives me my ratio of my indicator components. Because isn't this kind of a buffer in any way? It's weak acid and has a conjugate, right? So any weak acid with a conjugate could act as a buffer.
It's 1 to the negative 7.
Right? Yep. Or to make this a little bit probably easier for us to understand, what you have is the ratio is really 1 over 10 million. What color do we have? We're colorless. I have 10 million of my acid form and only 1 part of my basic form. So the question we should probably start asking ourselves is, when can the human eye detect a color change? That's the question we should be asking ourselves. And I even remember in the lab where it was like, okay, is that a color change or is that not a color change? You kind of start playing tricks on yourself, you know?
I'm walking from light to change.
Yeah, I know. Yep. And so, because you didn't want to really mess it up, and that's why usually using a pH sensor is the best way to do this. But having the color change indicator in there as well also kind of gives you like a heads up. Hey, we're getting close to the equivalence point. So, here's when the human eye can detect. Okay? The human eye can detect a color change when your ratio is 1 part to 10 parts.
That way you can like guess there might be a change, or you can definitely tell there has been a change.
It's a 1 to 10 ratio usually has enough of a color change that it's noticeably detectable.
Okay, it's not just
Like faint, yeah. I mean, it might be, not drastic, but enough that you could tell.
Wouldn't it also depend on the color though? Or no?
Probably a little bit.
I know green is more shades of green, I can see than other colors.
Yeah, I don't know about that. Yeah, I'm not sure. That was what?
We heard about that in Bible,
What in that
about
Bible?
the creation of you and I. I can see like 150 different shades of green.
So why aren't they really called 150 shades of green?
That's why night vision is green. You can differentiate better with depth with different shades of green.
Fun fact.
Yep.
Rylan, the teacher, taught me something today.
Rylan, the trivia, useless trivia.
No, I wouldn't call it useless, that's
That one's
fascinating.
interesting. Usually it's pretty
You're waiting separately.
Okay.
But I don't know enough about these categories.
Why do I not have, do you
Yeah,
guys have,
sports, 'cause
do you have anything else in your
notes.
notes? I need to change.
I feel like
You go to
I get a Jeopardy and I get like, oh,
What is spring league baseball?
best quarterbacks of
What is
1914.
Bush League?
They didn't even have professional football, I'm pretty sure, in 1914. Maybe they did.
I
They did. I did not. I don't.
They have the NFL.
The NFL.
So, let's,
1914 is first
alright
year
guys,
of
da
football.
da da da.
First year of football.
So, if the human eye can detect a color change at a 1 to 10 ratio, let's say I have an indicator known as bromothymol blue. Okay? Bromothymol blue is yellow in its acidic form. Okay, and you can imagine what it is in its basic form. Called bromothymol blue. Okay? It has a Ka 1 times 10 to the negative 7. Okay? Suppose you put a few drops of the indicator in a strong acid solution. If the solution is then titrated with a strong base, at what pH will we notice a color change? Or at what pH will the color change first be visible? What do we have to keep in the back of our head for trying to determine the pH of this color change?
1 times 10 to the negative 6. The 1 times 10 to the negative. No.
That has to be a six.
We know that the ratio has to be a 1 to 10 ratio. Well, we can use our Henderson-Hasselbalch equation. First of all, what is the pKa of 1 times 10 to the negative 7? 7 plus log of a 1/10. Log of 1 over 10 is 1. So we would see a pH change at 8. No. Log of 1/10 is negative 1. Log of 10 over 1 is 1. Sorry. pH of 6. Now, we could have done this using this equation as well. But I personally think it's easier using the Henderson-Hasselbalch equation, although if you feel like you would rather use that equation, you absolutely can do that as well.
Is it always one?
Okay, great question. So she just said, is it always 1/10? Well, first off, what is the ratio? Acid over base or base over acid?
That's
You did 1 times 10, sir.
What'd you say, sorry?
base over acid.
Base over acid.
That's it.
Okay? Now,
Whoa.
in this situation, when you have a 1 to 10 ratio, are we titrating an acid or are we titrating a base that will give us this? Yes. Because we have more acid and we're going to see a color change when some of the base starts to become noticeable. Does that make sense? If you were using the same indicator, but you were titrating a base, what would your ratio be? 10 over 1. Does that make sense? So, I'm glad you asked that because that's how we're going to try to, this is how we're going to try to figure out which indicator to use. So if you were going the opposite way, what you would have would be, you would have a pH of 8.
So what color is it? It's from 6 to 8. Whatever color it was.
It's gonna be in between.
Oh.
Right, like it's going to be a mixture of yellow and blue. But you would notice, right, like you would start with yellow here, and it would start to become a shade of blue. You would start with blue here, and it would start to become lighter toward the yellow shade.
Would it appear green in the middle, or did it go
Yeah.
all yellow,
probably.
all blue.
Well, if you added drops slow enough, you probably could get to a point where it was very green, yes. Yep. Now, so when determining, because remember, we have to choose an indicator that's close to the equivalence point. Right? Now we know that not all equivalence points are 7, are they? Didn't we talk about this when we were doing titrations of weak acids and weak bases? If you have a weak acid, its equivalence point will be basic, and if you have a weak base, its equivalence point will be acidic. So, when choosing an indicator, here's how we do it. How do I say that? We want our equivalence point to be plus or minus 1 of the indicator's pKa value. So, if our equivalence point was 7, we would want to use this indicator because we could see a color change at 6 if we were titrating an acid, and we could see a color change at 8 if we were titrating a base. So, let me see here. Let me pull out your book, turn in your book to 732. Okay, you see that big chart? What do you have is a whole bunch of color indicators. Okay? If you had an acid-base titration that had an equivalence point of approximately 5, which indicator or indicators would be okay indicators to use?
Methyl red.
Methyl red is probably the best one, but you could probably also use one more.
Crystal green.
Bromocrystal green. Crescel green. Okay, because remember there's some wiggle room because of that big upslope that we have in our pH curve. Okay, so you really could use a couple. Now, if you are doing, if you're using methyl red, what would probably be your pH, where you would see a or a color change if you were titrating a weak acid? Approximately what pH?
4.8.
I know it's hard to tell, but you would assume that the pH would change about 4. I know you can't really tell there.
Wait, 4? Didn't you reach 4?
No, I know, a little after 4, where you start seeing,
Oh, yeah.
because the shade would actually be a darker pink. Yeah, like it would be a darker version of that. And you would actually be able to tell. You'd be able to tell the slight change in the shade of the color. You're not like you think it would be more drastic, but you can still see even slight changes even in the shade of it. Okay? So, if you look at all the indicators, for the most part, you start seeing a color change either -1 pH or above 1 pH, plus or minus 1. Because if the equivalence point is about 5 on the methyl red, you're going to see a pH change of 4 or a pH change of about 6, depending upon whether you're titrating an acid or a base. Okay? So, let's say that we have this situation. Might even be able to get really low. Let's say we had 100 milliliters. Now the volume really isn't that important. 0.1 molar HCl, and we're titrating it with 0.1 molar OH, NaOH.
But wouldn't you adding the indicator affect the overall pH?
You only need to add a couple drops of indicator to see a color change. So and usually they're very weak. Well, it depends, but they're weak enough that they don't really change the pH that much. That's a good question. Okay, let's say the equivalence point. First of all, where is the equivalence point? You should know this. Not the volume. What is the pH at the equivalence?
Seven.
Okay, so pH of 7 at the equivalence point. Okay? Initially, what will I have? What form will my indicator be in? Now I'm not asking what color, what form, acidic or basic. Okay? Initially, I'm going to be in my acidic indicator form. Now, depending upon what indicator we choose, that might be a different color. Okay? But as we continue to add more OH, some of this acid form of the indicator will be converted to the basic form of the indicator. Okay? So the pH change will change rather slowly at first because of our pH curve that we're used to, and then we'll see a huge upswing with our indicator in the middle. Okay? If we want an indicator to change color at a pH of 7, what would the indicator's Ka value need to be? I'll say it again. If I want the pH to change, or if I have the equivalence point of 7, what indicator? Well, okay, I can see how you might want to use 1 times 10 to the negative 7. Okay, but if I want to actually see a color change right at the indicator, I'm going to want a pH. Yeah, you're right. And if I know my equivalence point is at 7, I want my pKa. That's an awful 7. I want my pKa to be 8. If I'm in the basic form, I want my pKa, well, my pKa would still be 8, but my color change would be 6 or 8, depending upon whether or not I am going from the acid form or going from the basic form. Okay? So I think in your homework, do you guys know what your homework problems are? 3. Okay, so in here you're just looking for what the color changes are. What other questions do you have? 67.
Probably the one.
Okay, so in 67 you're going to want to figure out what the equivalence point pHs are in those different problems. So then you can go identify what indicator to use. Does that make sense? Okay? So you have to go back to 51 and 53 to find your equivalence point pH. But you can find that in the back of your book, correct?
Yeah.
Okay? Is that it? Just those 3? 71, 73? Okay. Yep. Should be able to answer those questions. Alrighty, we're done. Because we're saying at equilibrium,